Hello everyone. In our lecture series based on broadening of spectral lines, today we are going to discuss Doppler broadening. We have discussed natural broadening, collision broadening, which are examples of homogeneous broadening. And today we are going to discuss the example of inhomogeneous broadening, which is Doppler broadening. Now, as we know that inhomogeneous broadening is that broadening mechanism in which different atoms behave differently. So this type of broadening, we will find that atoms are behaving differently. Till now, in natural and collision broadening, we saw that the behavior of atoms was similar. And those broadening mechanisms, those broadening in lines were due to the inherent nature. In natural broadening, we saw how lifetime of excited state results in the broadening of spectral line. In collision broadening, we saw that how, because atoms are moving randomly and they are never stationary, so how does the collision results in broadening of spectral line? And today we are going to discuss Doppler broadening. This is related to the velocity of atoms. Let's start. Now we know that atoms, they are never stationary. They are always in constant motion. They are moving randomly. If we are talking of solid, then we can see that atoms, they are tightly packed, but even in that situation also, they are not stationary. That stationary situation would only arise at 0 Kelvin, the absolute zero temperature, when everything just comes to a standstill. So here you can see all these things are showing the vibration of atoms. So even if solid has a definite shape and definite volume, and we say that atoms are packed, but still they are not stationary, they keep on vibrating about their mean position. So some sort of motion is definitely there. Then we have liquid. When we say that now we have loose atoms and they are free to move anywhere, and liquid doesn't have a fixed shape and it just takes the shape of container in which whichever it is poured. You can see the space increases between the atoms and they are moving. They always move. And in gas we find that there is more space between the atoms or the molecules. The intermolecular space increases, and obviously they have the freedom to move anywhere. All in all, the motion is always there, no matter which state of matter we are talking of. Further, this motion is also governed by the temperature. As you can see here, if we have low temperature, in that case, the movement would be low. They won't be moving that fast. As we know that temperature directly increases the energy of the atoms or molecules. Temperature affects the kinetic energy of atoms or molecules involved. If temperature is low, then kinetic energy of the atoms would be low and they would be moving because motion is always there, but they won't be moving that fast. And the effect due to motion will not be there. Any dominating effect due to or any other significant effect due to motion of atoms would not be there. And if we raise the temperature, then kinetic energy of atoms or molecule increase. As you can see here, now they are moving really fast. They start moving really fast. The intermolecular forces of attraction also increases. Their speed increases and they keep on hitting each other. Because we studied in collision broadening. Collision broadening happens under the cases of high pressure or high temperature, because in both the situations, in high pressure, we have lots of atoms or molecules together in a small space, definitely they would be hitting each other. And if we increase the temperature, then also the kinetic energy of atom would increase and they would be hitting each other. So all in all, the randomness or the random motion of atoms depends on the temperature of the medium. If temperature is increased, the kinetic energy would definitely increase. So the Doppler broadening is a case of inhomogeneous broadening. That means different atoms would be moving at different speeds. This is the thing. As we say that this is a case of inhomogeneous broadening, that means different atoms would be showing different behavior. In this case, the different behavior is basically the different speed, the different velocities at which the atoms would be moving. All the atoms would not be moving at same speeds. They would be moving at different velocities. Velocity and speed I would be using because here I'm not concerned much with the direction. It's all about the motion that we are concerned with. So we cannot expect all the atoms to move at same speed. This never happens. Even if the sample is same, even if the sample consists of atoms or molecule of one particular element only, even then all the atoms never show same behavior. That means all the atoms never move at same speed. This is by default characteristic. We cannot control it. This kind of difference in behavior will always be there. And also, even if we consider any particular case, especially as I'm concerned with the temperature case here, because we are saying that this effect is more dominant when temperature increases. That is a situation when Doppler broadening would show its effect in the spectral line plot. So when we increase the temperature, we never expect the temperature of all the atoms to get increased at the same time and at the same rate. You can take it by this example that when we start heating any substance, say water, in a pan, and we are providing the heat from the bottom of the pan. So the atom or molecule which are at the bottom, they would get heated first. Suppose we are heating water in this kettle, all the molecules which are getting the heat, the red ones, they are getting heated first. So they would move upwards. And the colder molecules, they would turn downwards. They would flow to the bottom. And as we know that hotter substance, hotter molecules, hotter gas, it rises upwards, and the colder air, it settles downwards, settles toward the ground. So similarly for the molecules, the hotter molecules, they tend to move upwards, and the colder one, they flow downwards. They take the position of the hotter ones. So at this particular moment, you would see that the temperature of all the molecules involved are not same. The molecules which are present here, they are having high temperature, comparatively high temperature. That's why I'm showing them with this red color as compared to the molecules that are present at this location. So if there is difference in temperature of the molecule, definitely there will be difference in kinetic energy of the molecule as well. So here, both these molecules, they are at different temperature, which thus implies different velocity. So this is an important concept to understand, that specifically we are studying this topic of Doppler broadening, which is often called thermal Doppler broadening, because temperature is involved here. The moment we increase the temperature, this effect starts showing up in the spectrum. So different temperature leads to different velocity, and this happens always. Whenever we take any sample, the temperature of all the atoms are never same. So if temperature is not same, their velocity will also not be same, because the formula that we have here for most probable speed, because most of the time, almost all of the molecule, like maximum percentage of molecule, they travel with a particular speed, but not everyone. So that's why we say most probable speed. That's denoted by u. Then this is given by 1 by 2 mu square is equal to kt. Okay, and now this is particularly the kinetic energy, and this is the temperature. K is the Boltzmann constant. So you can see here that kinetic energy depends on temperature. As K is the Boltzmann constant, it has a fixed value, it always stays the same. So basically it's the temperature which affects this kinetic energy. If temperature increases, kinetic energy would also increase, because U and T, they are directly proportional to each other. U determines the speed. Okay, U is the speed, and U square multiplied by m, and half of it gives us the kinetic energy. So it is directly linked to the temperature. So if we increase the temperature, velocity or speed of the particles of the atoms would also increase. But this word is very important, that most probable speed, that whenever we are taking any sample, most of the atom would, as if they are of same gas or any same element, if they belong to same category, then they would try to behave in similar manner, but still they never behave in the same manner. All of the atoms would never behave alike. So most probable speed, most of the atom, maximum percentage of the atom would try to move with same speed, but still there would be fraction of atoms that would be moving at some different speeds, and that is governed by temperature. If you increase the temperature, so the atoms which are at higher temperature, they would be moving faster than the other atoms. As we are studying the spectral lines, we obtain spectral line only either during absorption or emission of radiation. We were studying it like that when, suppose we are getting emission lines, we are studying emission spectrum, so atom would be jumping back to some lower energy state and some photon would be emitted. But the situation is not always like this, that you have a fixed energy levels and atoms are sitting there just stationary. We know that atoms are never stationary, they just keep on moving. And if we are having a gas, then definitely they would be moving. You cannot expect an atom of a gas to just sit idle. So most of the emission of radiation that occurs by an atom, that occurs during the movement. The atom is moving, it's just going, and then the emission of radiation happens when it makes transition from higher level to lower level. But that occurs during movement, during motion of atoms, and motion is somehow linked with temperature. And that's the reason that we are studying a lot about temperature here, and which is actually affecting the speed of velocity. Since the emission of radiation occur during motion of atoms, especially in case of gases where atoms just keep on moving randomly. They are moving in all directions. Atom, they can move anywhere. And during that motion, they might jump from higher energy level to lower energy level also. And then radiation would be emitted. So all that emission occurs during the motion of atoms, which further depends on temperature. Okay, so this particular thing should be clear. Now we know that the speed of atoms depend on the temperature. The temperature of the medium would govern the velocity of the atoms involved, and most probable speed u, that depends on temperature, as 1 by 2 mu square is equal to kt, that is kinetic energy is equal to kt. So we can obtain this velocity distribution of atoms with given speed by Maxwell Boltzmann distribution. So Maxwell Boltzmann distribution, this is a very popular distribution law given by both these scientists. It tells us the number of atoms which would be moving at a given speed. So they tell in a particular sample how many atoms would be moving at one particular speed, say v1 or velocity, and how many atoms would be moving with velocity v2. Like whatever velocities are involved there, how many atoms would be contributing to that particular velocity. So this is the Maxwell Boltzmann law of velocity distribution of any particular gas or sample that we have. They just tell us what's the number of atoms that would be moving at a particular speed or velocity. So this is very important to distinguish between the atoms which are moving at different velocities. They gave us this expression also. This expression gives us the number of atoms which are moving with a particular velocity v. So we can find all the count of atoms which are moving at particular velocities. This is the general expression. This capital N is the total number of atoms involved. How many atoms are there in the gas or the sample that we have taken. So whatever is the total number of atoms present, that is governed by N. And then m naught, as you can see here, m naught is the mass, atomic mass. This is what we need to know. And then to number pi, k is Boltzmann constant again, T is the temperature, and here again we have this velocity factor, again the Boltzmann constant and the temperature, and this is the atomic mass. This expression gives us the number of atoms moving at a particular velocity v. We can use this expression to find how many number of atoms are moving at a particular velocity. All we have to do is just change this factor. Everything else is same. See, whatever sample we take, we would be knowing in advance what is the total number of atoms present. So this quantity is also fixed. Then we also be knowing what is the atomic mass. So this is also fixed. This is also fixed. Then 2 is a number, pi is a constant, k is again Boltzmann constant. These all are constants. And then one thing is temperature that we will fix in the beginning. After that, this is the exponential term. And again, here we have the atomic mass, the velocity, 2, k and t. So all these things we are going to fix in the beginning. All we have to change, this is the changing factor, the changing variable. Rest of the variables, they are fixed in the beginning. Right before doing the experiment, we are going to know that what is the total number of atom present, what is the atomic mass, and what is the temperature at which we are doing the experiment, at the temperature at which the gas is kept. For example, we are studying about a gas sample. We would be knowing its temperature in advance. So all we have to do is just change this value. We will substitute different values of velocity and we would be getting different values of NVDV. That means different number of atoms. So at particular velocity V1, we would get number of atoms N1. Then the atoms which are moving at velocity V2, we would get their number. The atoms which are moving at velocity V3, we would get their number. So in the same way, we would get all the number of atoms which are moving at different velocities. In this way we can find. So this is very important. If you don't know, if you haven't read what is Maxwell Boltzmann law of velocity distribution, I would make a video on that too. So this expression we just need to know, this is only for understanding that there is a distribution law which tells us that in a particular sample, all the atoms never move at same velocity. The velocity keep on changing and we can find the number of atoms moving at different velocities. And temperature is one of the important factor here. The kind of graph that we obtain in Maxwell Boltzmann distribution law is something like that. So the distribution gives us a graph where velocity is on the x-axis and dn by n, this is the fraction number of atoms which are moving at a particular velocity upon total number of atoms. This is just the fraction. And the graph obtained is this bell-shaped curve again. And here, since if we are talking of a particular sample, most of the atoms are alike. They all would be having same atomic mass. So most of the characteristic would be same. So they would try to move at same velocities. So maximum percentage would be moving at a particular velocity, which we call most probable speed or velocity. That's why we get a peak. That peak is for that most probable velocity. So maximum number of atoms, they would be moving at a particular velocity that we can see here. And then since if we are getting a curve like this, that means this point would be corresponding to some other velocity. Let's say V naught, and this point would be corresponding to some other velocity, say V1. And here, if we join it to this y-axis, then we can get different number of atoms. So by this graph, we actually get what is the number of atoms that are moving at a particular velocity. But still, the most probable, the maximum number of atoms would be moving at most probable velocity. So the most probable thing is always there. We saw that normally in the spectrum we obtain lines, the peaks that we obtain, we have the maximum peak or the central line which corresponds to natural frequency nu naught, and most of the photons emitted, they are having the frequency nu naught. So some dominating feature is always there, that most of the atoms prefer a particular behavior, but not all. So this not all thing should always be kept in mind, that all of the atoms never behave alike. And that's the reason that we see this broadening. This curve is all because different atoms, they are moving at different velocities. Now the name of this broadening mechanism is Doppler broadening. This Doppler broadening. So this Doppler word, we have read this before also in our earlier physics courses, the Doppler effect. So definitely this Doppler broadening has some relation, has some connection with that Doppler effect. That's why it has got its name, because we often use the similar terms, similar names in defining similar phenomena. So let's study what was that Doppler effect. Doppler's effect is the apparent change in the frequency of radiation due to relative motion between source and observer. So this apparent change means it's not the real change, because ultimately if we are talking of sound, that sound would be emitted at a particular frequency. It will not change in between. And if we are talking of light, even the light emitted would also be having a particular frequency. So this apparent change means to an observer, this change appears. The observer feels that there is some change in the frequency, though in reality there is not any change. And why is that change? The change is due to relative motion between source and observer. Now we have studied special theory of relativity. It states that all the motions are relative. Nothing is at absolute rest or in absolute state of motion. You must have studied this. This is the famous special theory of relativity given by Einstein, which tells us that all the motions are relative. You cannot say that a particular thing is at absolute rest or a particular thing is in constant or absolute motion, that it is always moving and it is some, and the other thing is always at rest. This never happens. All the motions and all these states, all the physical situation or condition of the object, the state in which the object is, it's relative. Something is at rest with respect to some other thing, or something is in motion with respect to some other thing. So this Doppler's effect is the apparent change. That means it just appears to be, though it is not there in reality, in the frequency of radiation due to relative motion between source and observer. It is due to the motion between the two. Suppose the observer is at rest and source is moving towards it, or source is at rest and observer is moving towards or away from it. So due to that relative motion, this effect arises. And due to this relative motion, there is change in frequency. The frequency is the thing which changes. And frequency is basically what the energy changes. E is equal to h nu, where h is Planck's constant, which is a constant. So if frequency is changing, that means the energy of that particular radiation is changing. So if we consider the case of sound, here this example you can see it is for sound waves, the Doppler effect in sound. Here you can see this ambulance is moving towards this person. So the horn blown by this ambulance, it has a particular frequency. But for this observer, that sound would appear to be of high frequency, very high frequency, as this ambulance is moving towards this observer. And since this ambulance is moving away from this observer, this girl, for her, the frequency of sound would appear to be lesser. Though the frequency of the horn of this ambulance is same, it's fixed. It has a particular frequency, a particular value. But it's the apparent change of the value for these two observers, this man and the lady. These are the two observers, and there is relative motion between them and the ambulance. Here, the ambulance is moving towards the observer, and it is moving away from this lady. So it is moving towards the man and moving away from the lady. As it is approaching this man, the frequency of the horn would appear to be higher to this man. The pitch would increase. Pitch is basically the frequency of the sound. So the pitch would increase and the volume would appear to be higher. So the frequency would appear to be higher to this man. But since this ambulance is going away from this lady, the frequency would appear to be low of the horn blown by this ambulance. This would find it to be at lower frequency, but man would find it to be at higher frequency. Though there is fixed frequency of the horn, but still for both these observers, the frequency would appear to be different. Similarly, we have the case of light waves as well. In light waves also same thing happen. Here again we have two observers. Now here for this girl, this light is moving towards her. Okay, you can see this arrow is showing that this light is basically moving towards the girl and moving away from boy. So here we have the away from situation, and here we have the towards situation. And you can see that as the waves are approaching the girl, they are getting closer. All the waves, they are just getting closer. You can see the closeness of the waves. And here, they are wider. There is wide separation between the waves. So, in case of light, due to this Doppler effect, because ultimately, again, light also, whatever is the energy of light, we talk in terms of frequency. Again, for these two observers, the frequency of light would appear to be different, but not in terms of sound, but in terms of light. So the light, whatever is the frequency of this light, to both these observers, the frequency would appear to be different. So in case of light, what is the meaning of different frequency? The meaning is the color. The color of the light would appear to be different. So in case of light waves, the Doppler effect results in different color. To both these observers, the color would appear to be different, color of the light, as the source of light is not fixed, it's moving. The source of light is moving, it is moving towards the girl, but it is moving away from the boy. So due to this effect, there will be some apparent change in frequency for both these observers. They would experience some change in frequency of light. And the change in frequency of light means what? The change in color of the light. So the color of the light would appear to be different. to the girl, if here you can say as light is approaching the girl, so the waves are really close to each other, and we can see that the bends, the crest and troughs of the waves, they are quite close to each other. That means the frequency is high here. So here frequency is high. So high frequency means what? This relates to the bluish zone of the spectrum or of the Vibgyor if we talk of. We know that red color has the longest wavelength and blue color has the shortest wavelength. And wavelength and frequency, they are inversely related to each other. So if blue has the shortest wavelength, that means blue has the highest frequency. And if red has the longest wavelength, that means red has the the lowest frequency. So here we have low frequency, and here we have high frequency. And high frequency corresponds to bluish color of the light, and low frequency corresponds to reddish color of the light. So whatever is the light source, whatever is the frequency of the light source, if it's approaching towards the observer, so here due to the Doppler effect, the frequency would change, and frequency is increasing as it is approaching the observer, and observer here is the girl. If it's approaching the girl, the frequency would increase, and high frequency means blue light. Here we are talking in terms of color. In case of light, we talk in terms of color because we are concerned with the color. So the color would appear to be blue to the girl, but since this light source is moving away from the boy, again there would the frequency of the source would appear to be different to the boy. And different in what sense? That the frequency would appear to be lower than the actual frequency. To girl, higher frequency would be visible, and to boy, lower frequency would be visible. However, in reality, frequency of the source is not changing. So this phenomenon of Doppler effect totally depends on the observer who is viewing the source of light. And also it depends on the relative position between the source and the observer. Thus, we observe this Doppler effect in both sound waves as well as in light waves. In sound waves, what we observe is change in sound. The sound, its intensity appears to be different. Of course, we often say that the pitch of the sound is different because that is also related to frequency. So if the vehicle is moving towards the observer, then the sound of the horn blown by that vehicle would appear to be really high in pitch to that observer, but the observer from which the vehicle is moving away, that observer would observe quite low frequency sound. And similarly, in light waves, the frequency is understood in terms of color. So if something is high in frequency, if light wave is high in frequency, it would depict bluish color, and if it is lower in frequency, then it would depict reddish color. So we often call this phenomena as blue shifted and red shifted. This is a very popular phenomena that we observe. It's red shifted or blue shifted. We say the light has blue shifted, or we say that the wavelength has blue shifted or the wavelength has red shifted. We can say because we know that wavelength and frequency, they are linked to each other. Similar Doppler effect is observed by astronomers when they study galaxies. So the data or the spectrum they obtained by telescope tells them that the spectrum obtained from galaxies gives a reddish hue. Most of the time, the spectrum that the astronomers obtain from different galaxies, from stars which are residing in different galaxies, the color, the most prominent color is the red one. Whatever spectrum is obtained, there is a reddish hue in that spectrum, which is a clear indicator that galaxy is moving away from us, that the light is approaching from that star whatsoever is in the galaxy. But since the light which is coming appears to be reddish in color, this tells us that the galaxy is moving away from us. And this is a known phenomena, and it is actually happening as our universe is expanding. So our universe is expanding and all the galaxies, they all are just moving away from us. So if we study the light spectrum, the spectrum of any star which are there in the different galaxies, they appear to be reddish in color. So that's why we say that the light has been blue shifted or red shifted, and in most of the cases when we study stars and their spectra, we say that always the light is red shifted as they are moving away from us at very slow speed, but still they are moving away from us. Coming back to atoms, as we are studying Doppler effect in atoms, how we observe this Doppler effect and how does this Doppler effect results in the widening of spectral line. So now the atoms, they are randomly moving. If we are considering gas molecules or atoms, then definitely they would be moving here and there. And then we have taken this detector. Detector would be observing all the atoms. Now here we can say that this detector is observer. He is going to observe all the atoms. Now obviously, as we know that if we take a closed entity and all the atoms, you can see their motion have been indicated by arrows. Some of them are moving towards detector, some are moving away from detector, and some are moving in other direction. Now again, this Doppler effect would enter in. Now those atoms which are moving towards the detector, now detector is the observer, so he is going to observe the frequency of spectral lines, whatever are going to be there, because ultimately while moving, while in motion, atoms would make transition from one state to another, and then photon will be emitted. So that photon which will be emitted, originally it might be having some frequency like nu. See, the actual frequency of photon emitted when atom makes transition from one level to another, it would be nu. This we know, the atom knows. Atom would say that the radiation emitted is having frequency nu. But to this detector, this frequency would not appear to be same. Why? Due to Doppler effect. There is relative motion between detector and the atom. In this particular case, detector is always at rest because we have fixed the detector at one particular location, and atoms, they are just moving randomly. Now, whenever atom would make transition from one level to another, we know a photon will be emitted. Now, suppose when the atom makes transition from one level to another, photon emitted is having the actual frequency of nu. Suppose nu is the actual frequency, the original frequency of photon emitted. But to detector, this frequency would not appear to be the same. Detector would consider it or would record it to be slightly different. And that difference would be delta nu. It's not such big difference, but it is there. So delta nu is the difference. Now suppose this atom, you can see this green one, it is moving away from the detector. Now we know due to Doppler effect that when something, suppose in light, you can say that if something is moving away, like here to this man, this source of light is moving away. So now he observes lower frequency of the source of light than the actual frequency. So similarly, now this atom is moving away from the detector, but in the meantime, it would definitely make transition from one level to another, and photon will be emitted. And atom knows in reality the frequency of that emitted photon is nu. But since due to Doppler effect an atom is moving away from the detector, detector would observe this frequency to be lower, because whenever there is relative motion between source and observer, and source is actually moving away from the observer detects lower frequency than the original. So now nu minus delta nu would be the frequency detected by detector. Here detector is our observer. Similarly, if you consider this atom, this red one, which is moving towards the detector, so now during its motion, it would make transition from one level to another and photon will be emitted. But now again the original frequency of photon is nu, but since there is relative motion between atom and detector and atom is moving towards detector, so the Doppler effect would come into action and detector would observe the frequency of photon to be nu plus delta nu. So delta nu is that small difference which is arising due to this Doppler effect, due to relative motion between the two. And we know that velocity, like for any particle, we use this relation, and this c is basically the speed of light. So if we are considering photons, we usually go for the formula c equal to nu lambda, because c stands for speed of light, and we say that light is basically made up of photons. It's nothing but group of photons moving. So some atoms would be moving toward detector when they emit radiation, some would be moving away, and other would be moving in some other directions. So for all of them, they would be emitting photons, but detector would observe those photons to be having slightly different frequency than they actually have. Thus, every spectral line emitted is Doppler shifted relative to the detector, resulting in small change in the observed frequencies. Because we know whatever photons are getting emitted, we will get a curve. Curve corresponds to the number of photons emitted having a particular frequency. So basically on the x-axis we have frequency, and on the y-axis we have intensity or the count. So we just get peaks according to how many photons of particular frequency are emitted. So depending on the relative motion between atom and the detector, photons emitted, they would be having slightly different frequencies for the detector. So always keep this in mind, that maybe all the photons, they are getting emitted of same frequency. Though we know that natural broadening and collision broadening is also there, which would result in the emission of different photons. We know that. But now this Doppler effect is also there. So whatever photon will be emitted and the spectral line that we would obtain, all of the spectral line, maximum of the spectral lines, they would be Doppler shifted related to the detector. And this spreading of spectral line, obviously we will get broadened peak due to this, because now we will not be getting peak corresponding to fixed central frequency. In fact, there would be maximum or like large number of photons having frequencies quite near to but not similar to nu naught. We know nu naught is the central frequency, which is the exact one, but we would be having nu naught plus delta nu or nu naught minus delta nu as such. Basically, observer is the detector and source is the atom which is emitting radiation. And again, you can see here that nu naught is the actual central frequency, but we will be obtaining these some other frequencies as well. Here you can have a look at this example. This is for emission line spectrum at lower temperature, and the second one is emission line spectrum with thermal line broadening, because we know that temperature has the effect. Temperature effect we include whenever we talk of Doppler broadening. We know that maximum time the emission of radiation by an atom occurs during movement, and the mean particle velocity is related to temperature of the medium. More the temperature, more the kinetic energy of the atom, and rest we already know that its motion would result in Doppler broadening. So here we can see the emission line spectrum with narrow line. Here the temperature was lower. So we can expect that atoms, they are moving slowly. And if they are moving slowly, though the motion will still be in random direction, but that won't be too much significant for the detector to actually detect some significant change in the frequency. Atoms are still moving, but they are moving really slow, and some might be moving toward detector, might be moving away from detector, but their motion is not that significant because the speed would be really slow, and thus very negligible change in frequency would be observed by detector. But the moment you raise the temperature, here you can see that the spectrum we have obtained now has broadened. So the lines which were quite narrow before, they have broadened now. So this is because of the thermal line broadening, we call it, because of the temperature increase. Once we increase the temperature, of course the motion between different atoms would change, the kinetic energy would increase, and then they would start moving either very rapidly towards detector or very rapidly away from detector. And then because velocity is also there, we know u, if we are considering the velocity of atom, so now different atom, they will be moving with different velocity, and of course the velocity would be high because now you have raised the temperature. So there are different atoms, they would be moving at different velocities, and then of course whenever they would emit radiation, the detector would detect different frequencies for similar type of emission of radiation. So that's why we say that when atom is moving towards the detector, emitted radiation will be shifted to higher frequency, and when atom is moving away from the detector, the emitted radiation will be shifted to lower frequency. So actual frequency is different and observed frequency is different. And here different atoms behave differently, and that's why we call that this is heterogeneous broadening mechanism. This is an example of heterogeneous broadening because here different atom, they show different behavior. All will not be moving with same velocity because all will not be having same temperature, and we already know that whenever we provide temperature to any medium, it's not that it quickly spreads all over. No, some of the atom might get heated first, some might be later, so some must be hotter than the other, and if one of the atom is at higher temperature, its velocity, its kinetic energy would definitely be higher than the rest of the other, and then that would affect the emission of photon and its frequency. So this is how Doppler effect results in broadening of spectral line. So all in all, we obtain all three effects. Natural broadening is also there, that is the inherent feature, but it is not that dominant. It still gives broadening, but that is not much broadened. But collision and Doppler are the dominant one. So this was all about Doppler broadening, and in the next video we'll discuss the derivation of Doppler broadening, which would actually result in the expression for delta omega, which is our line width. So stay tuned. Thank you.